All right, folks, here we are at section 4.17, talking about something called the perceptron algorithm. So this is one of the early examples of these learning units. These units with adjustable parameters look kind of like the brain. The units in the brain may be loosely inspired by them that could learn interesting discriminations. And the basic idea, I mean, the name itself is kind of interesting, right? You can think of like electrons and protons and neutrons as being kind of the basic particles of matter, and now perceptron as a kind of basic particle of perception. And the simplest setup of this was one where you essentially had, you have a unit and it's taking inputs with some set of weights, W1 to Wn, and it has some threshold, and then it's giving you -1 or +1 based on whether the input is above the threshold or not. And you can imagine then using that and trying to find weights where you could actually then do interesting discriminations. Like, let's say if your inputs were coming from, some grid of pixels, as we'll see, you can do like, does that grid contain the letter C? Now, obviously, these days for us, that seems like very commonplace, but back then in the 60s, I think this was a very cool idea, and to show that one could actually do this, like if a discrimination could be made showing that, not only do you have a unit that could potentially make that discrimination, but having an algorithm that, when the discrimination is possible, will actually, will provably find that discrimination, will provably separate your A's from your B's. That was pretty cool, and still is pretty cool. So I think it's kind of a useful, simple system to learn about. So let's get into it. And you guys can see everything. Very good. So let's just erase all of that. All right. Good. So another example of a linear discriminant model is the perceptron of Rosenblatt. So again, we're talking about linear discriminant. So we're looking for a weight vector that will project our inputs, maybe after some nonlinearity, a fixed nonlinearity, into a binary decision. Occupies an important place in the history of pattern recognition algorithms. It corresponds to a two-class model. Okay, so we've just got, that's where the binary aspect comes from, in which the input vector is first transformed using a fixed nonlinear transformation, so that's phi, to give a feature vector phi of x, and we've already seen this in previous chapters, like chapter 3. And this is then used to construct a generalized linear model of the form. So we've got this kind of like linear term inside, linear in the weights, and then we're getting some transformation on the output. And the transformation is kind of what we already talked about. So it's +1 or -1. It's just it's a step function. So here's our input, and it's just going to go, I suppose it's going to look like this. So there you go. It's going to be a sharp a binary transitioning, but going from -1 to +1. We'll see the sign is important, makes our life a bit easier. But this flatness of this function is going to make learning difficult. And so we're going to be using a different algorithm than, let's say, normal gradient descent to learn how to learn the weights that we're going to need. So the whole game is going to be to learn the weights to match the output labels to what we're given. Okay, so let's continue. The vector phi of x will typically include a bias component. Okay, in early discussions of two-class classification problems, we have focused on target coding scheme in which t belongs to 0, 1. But for what we're going to be discussing here, we're going to have t be +1 for class 1 and -1 for class 2. So that's going to be, well, you'll see why that's useful. I mean, you can always do it the other way, and there'll just be some little conversion factors you have to incorporate, but it's just easier to do +1 or -1. Okay, so now it says that, and the cool thing is the perceptron algorithm, right? So how are you going to actually learn these weights? Now, the algorithm used to determine the parameter w of the perceptron can most easily be motivated by error function minimization. Okay, so we've seen that before, but what error function? So a natural choice of error function would be the total number of misclassified patterns, right? So if you want to reduce that. However, this does not lead to a simple learning algorithm because the error is a piecewise constant function of w, with discontinuities wherever a change in w causes the decision boundary to move across one of the data points. So all that's saying is, let's say you've misclassified a particular point, so you've got some error there. Well, if you typically, unless you're on the exact boundary, which will almost never happen, typically changing w by a small amount won't change the number of misclassified patterns. So there's no gradient signal, and that's just coming from the fact that this function that you have is just flat, right? So if it was flat and giving +1, where we're supposed to be giving -1, well, if you change w by a small amount, it'll still give +1. So there's no slope there to actually go up or down. So you can't actually do our normal gradient descent thing. So you still want to measure these misclassifications, but using that raw number as a gradient to go down won't work because there is no gradient. The error is a piecewise constant function. So that's what we mean of w. So for a whole bunch of for a whole set of w's, it'll have that pattern will be misclassified, and then you'll cross some boundary, and now maybe that error that example is now classified correctly, so your thing will drop by 1, and then you'll have another flat surface where your misclassifications don't change until you cross some other threshold. So it's a very hard surface to actually do learning in the usual way. Okay. Methods based on changing w using gradient of the error function cannot then be applied because the gradient is 0 almost everywhere. And I mean, I think it just isn't even defined at those other points, those boundary points. So we therefore consider an alternative error function known as a perceptron criterion. So this is useful to know. I mean, to show, okay, it's useful because it will work. We're not going to talk about the proof, but it will work and will allow w to be learned when you can make the classification. But it's also nice to see how you would, especially in these classification settings where the answers or the error functions are discrete, how you would work around, how you would change your error function so that you could get a learning signal. So to derive this, we note that we are seeking a weight vector w such that patterns x of n in class C1 will have this projection be positive, so that after the step function they become +1, whereas the patterns xn in class C2 will have this projection be negative, so that they will get -1. Using t belonging to the binary and to this +-1 set, and that's where it becomes useful. Target coding scheme. It follows that we would like all patterns to satisfy this product to be positive, right? So whenever this is positive, we want t of n to be +1, and whenever this is negative, we want this to be -1. So we always want this product to be positive. The perceptron criterion associates 0 error with any pattern that is correctly classified. So whereas for a misclassified pattern x of n, it tries to minimize the quantity this. So one way to think about that is where we want to want this quantity to be positive, so we want to make this larger, or alternatively, we want to make the minus of it smaller. So that's kind of where the minimization comes from. And now let's see if it actually works. So let's see, we've got t of n. Let's say we've got t of n being greater than 0. And let's say this quantity here has to be less than 0 for us to be considering it, because we have to be getting the wrong sign. And now this is -1. So this whole thing is positive, and now we want to minimize it. So if we increased, so what would happen? So if wt phi x of n, if we decrease that, so if we made it even more negative, then this whole quantity goes to, our error of n would increase, right? Because this would become more negative times the minus would become more positive, and would go up. So actually what we want is wt phi of xn in that case to increase, and it's negative, so that this would go to our energy, our error decreasing, and that's exactly what we want, right? So our quantity here is negative when the label is positive, so we actually want wt, that projection to increase. We want w to be more lined up with that particular pattern. Okay, so you're going to think of coming up with that, just checking it in 2 ways. So either by just saying, hey, we want to maximize that, which is the same as minimizing this, or looking at it on kind of a single label, level. Okay, and the other key thing just to keep in mind is, which also is kind of different to gradient descent, is that we're going to actually ignore patterns that are correctly classified. So we're only going to look at the ones that aren't correctly classified. So zero error with any pattern that's correctly classified. Whereas like in, other, like I think we had in the previous section we had regression, classification as regression. And there, even if a pattern is already correctly classified, you still include it, and that can be good and bad. Whereas here, you're only working with the misclassified patterns, and that's kind of indicated actually by n being in the set of this capital M for misclassified. So we're trying to minimize this quantity. Okay. The contribution to the error associated with a particular misclassified pattern is a linear function of W in regions of W space where the pattern is misclassified and 0 in regions where it's correctly classified. The total error function is therefore piecewise linear. So yeah, so that's kind of the key thing here, right? So instead of, we no longer have, we don't have like we're not dealing with this flat function anymore. We've kind of linearized the problem. So wherever it's being kind of misclassified, W is, this error now depends linearly on W. So now you actually have a function that you can actually minimize, which is useful. Okay, so the total, and then you just add them all up, and so therefore, so it's linear. So the total error function is therefore piecewise linear. In regions of W space where the pattern is misclassified, and 0 in regions where it's correctly classified. Yeah, so we're just kind of looking at this on kind of a single label level. And so you can look at this as a function. Let's just look at for a single pattern. You've got the label, you've got this nonlinear projection, and I can consider all the different values of W. In some regions where W is actually, for that W, you're actually classifying things correctly, W doesn't even show up in the error function. So the error function will be flat. And then in other regions where it's misclassified, it's going to be linear in W. So you're going to have this kind of piecewise linear thing for one pattern. And then you just combine them for all the different patterns, and you get the sum of piecewise linear things will also be piecewise linear, and that'll be your total error function. So it'll kind of look like something like that if we kind of projected it along one dimension. And that's kind of workable, and at these you never have to deal with these kinked regions, so you often, just due to your step sizes, will always end up on one side or the other where you have a valid gradient. Okay. We now apply the stochastic gradient descent algorithm to this error function, and the change in the weight vector W is then given by, so you've got your new weight is equal to your old weight minus going down the error function some step size proportional to the gradient of the function with respect to W. We now have a gradient, so now it's WT plus, if we just look at this, we'll see that the gradient is just Wn T of n for a given example. Okay, that's where that's coming from. So you're doing it one example at a time. Where n is a learning rate and t is an integer that indexes the steps of the algorithm. Okay, now because the perceptron function is unchanged, if we multiply W by a constant, we can set the learning rate parameter eta equal to 1 without loss of generality. So all he's saying here is, look, we've got this like learning rate thing hanging around, which we typically have, but we can just talk about weights, divide everything by eta, and then you don't have to deal with this. Why is that okay? Well, it's because when we're actually computing the labels, all we care about is the sign of this projection onto the feature vector. So scaling by a positive constant doesn't change that sign. Therefore, we can just get rid of this dependence on eta. Okay, all right. Good. So that's just how you would do it. But now this interpretation is actually useful. So has a simple interpretation as follows. We cycle through the training patterns in turn, and for each pattern, we evaluate the perceptron function, so that's that thing. If the pattern is correctly classified, then the weight vector remains unchanged, whereas if it's incorrectly classified, then for class C1, we add the vector 5xn onto the current estimate of the weight vector, while for class C2, we subtract the weight vector. So that's just coming from the fact that T of n here is positive or negative, right? So if you're in the positive class, you're going to be adding that feature to the weight, and if you're in the negative class, you're going to be subtracting. And that kind of makes sense, right? Like you want the W to line up with all to be in the same direction as all of the positive features, and then in the opposite direction as the negative features, and that's exactly what this is doing. So it makes intuitive sense. And yeah, so there's an example of this. Let's just before we jump to the example, let's just cover this next paragraph. So if we consider the effect of a single update in the perceptron learning algorithm, we see that the contribution to the error from a misclassified pattern will be reduced. And this is often kind of a tactic we will do to show that algorithms converge. We'll look at what happens after a single update, and we'll show that, okay, for example, sometimes there'll be like some function that we know to be positive, and we'll show that after every step its value is decreasing, so we'll know that it will like eventually converge, or will get arbitrarily close to zero, things like this. Here we're kind of in a similar situation, but there is a caveat. We'll see. Okay, so let's just see what happens. So we're looking at what is the projection of the weight after we've updated it onto the feature and then indexed by label, scaled by label. And we see that, okay, well, so you've got the old value, and now the new weight is just going to be 5n t of n, right? That's just coming from, it's been updated by that amount. So you've got the old weight plus the change. And you see that, well, this is just 5n tn squared. And so we know this is going to be less than 0. And so we know that the new value has actually been reduced relative to the old value. Okay, now our error function doesn't have, as far as I can tell from this, doesn't have actually a lower bound, so this can continue forever. But there's something called the Perceptron convergence theorem that says that if it's separable, things are separable, they will be separated in a finite number of steps. So it will eventually converge. But this is not one of those cases where you can say just based on the fact that that your value is lower bounded by 0, that okay, will always stop. You have to take a different approach, which we won't cover, but you can read all about it in the convergence theorem. Okay, of course, this does not imply that the contribution to the error function from other misclassified patterns will have been reduced, right? Because we just made a change relative to one of the patterns. Furthermore, the change in the weight vector may have caused some previously correctly classified patterns to become misclassified. Thus, the perceptron learning rule is not guaranteed to reduce the total error function at each stage. So that's the point. It's not always going to be decreasing it. And so the point is, okay, well, we've decreased it for 1. How do we know this will generally work? Like maybe I've made it better here, but worse elsewhere. But there's a theorem that says that if there exists an exact solution, let's highlight, if there exists an exact solution, so if the training data is linearly separable, then the perceptron learning algorithm is guaranteed to find an exact solution in a finite number of steps. And that's pretty cool, right? Because you've just shown that, up here, we've shown that it does the right thing in one case. Maybe it's an intuitive derivation for its update rule, but how do we know that it works? Well, it turns out that if the data is actually separable, you will find it with this approach after a finite number of steps, which is pretty cool. Note, however, the number of steps required to achieve convergence could still be substantial, and in practice, until convergence is achieved, we will not be able to distinguish between a non-separable problem and one that's simply slow to converge, right? So, important practical caveats. Even when the data is linearly separable, there may be many solutions, because you can imagine if you have a finite number of points that are separable, there's a whole infinite set of linear separations. And which one is found will depend on the initialization of the parameters and on the order of presentation of data points. For data sets that are not linearly separable, the perceptron learning algorithm will never converge. And you can just imagine why that is, right? You'll adjust the weights to 1, but then maybe it'll fix the situation there, but then some other unit will be on the wrong side of the boundary, and you just have to keep going back and forth, and you'll never know. And it'll just keep bouncing around, and you'll never find, it'll never steady. Because in principle, it would steady if it found no misclassified points. But if the points aren't linearly separable, then that'll never happen. So you'll always just be bouncing around. Okay, so let's have a look at how this works in practice. Let me make sure you guys can see this. Okay. All right. So the idea here is you've got your points, red, and some blue points, and points on this side are supposed to be on the red side, and points on that side are supposed to be on the blue side. Okay. So now we're going to pick one of the points. So, and here's our initial vector. Okay, our initial weight vector, we just randomly initialized it. Now we pick one of the points that's misclassified, so this is on the wrong side. All the reds are supposed to be here. And we say, okay, it's misclassified, so now we're going to add, because this is the plus side, we're going to add this pattern to the weight vector. So now the weight vector moves over here, and now it's updated. Okay? Now we pick another one of the points, so now this one is still misclassified, so now we take that weight vector and we add this feature. And now we finally get a weight vector there, and now everything's perfectly classified, algorithm stops. Okay, so that's basically how it works. And it kind of makes sense, right? You want points like this to be on the plus side of the weight vector. So every time it's misclassified, you just add that point to the weight vector, and eventually, if things are separable, it will kind of drag the weight vector to be pointing in the right direction. Cool. Okay, so let's yeah, this is also, I think this is like a really, I mean, we're just so spoiled today with all the tools we have. Like, this is an example of this perceptron in like a hardware. So like here they were they had some cameras, they were looking at this image and then like focusing it onto like a 20 by 20 set of photo cells to get a 20 by 20 input, and then like wiring these things by hand, and then setting the weights by like having these like variable resistors that were controlled by motors to adjust the weights automatically and show that the thing could learn. I mean, it's just amazing, man, the amount of work they did. And we can just do this in a few lines of code now. So if you're ever frustrated by how long things are taking for you, or how long your code is running, imagine that this could have been you working with this, in the physical hardware setting, I guess now 60 years ago. So how much things have come, and how much we should appreciate the tools we have at our fingertips, and what we could do with them. Okay. Anyway. Okay, so aside from difficulties with the learning algorithm, the Perceptron does not provide probabilistic outputs, right? And nor does it generalize readily to k is greater than 2 classes. The most important limitation, however, arises from the fact that in common with all the models described in this chapter, is based on linear combination of fixed basis functions. And we talked about why that can be limiting, and in high-dimensional spaces, what you want is you want to learn those basis functions. So essentially having kind of a multiple layer networks. Yeah, you can read more about that here. We just talked about the analog hardware implementation, just amazing. And finally, at the same time, the Perceptron is being developed, a closely related, I just call it an Adeline, which is an adaptive linear element. Yeah, there we go. Was being explored by Witcher co-workers, but a different approach to training was adopted. So yeah, you can find out more about that over here. Okay, so I think that was all I wanted to talk about in the Perceptron. Again, you will still hear about it. Perceptrons are still like very commonly used units, so it's good to know what they are, and it's good to know about this convergence theorem and kind of intuitively how this is working, and also how to set up your error function correctly in settings where you have kind of the naive application will give you a flat error surface. So kind of just splitting things up, looking at the case that are being misclassified, and then trying to reduce the input to the classification function in the correct way. Finally, yeah, here's Frank Rosenblatt himself. I think he died tragically young, about 41, I think, in a boating accident, but he kind of got all this going, so might be interesting to kind of read about him as well. All right, very good. So I think, I think next time we will start again with now changing gears to now probabilistic generative models. So we've been working on these discriminative models, and now we're going to be talking about the probabilistic models, in particular the generative version of those. Okay, so hope you've learned some stuff today. As always, just appreciate all the comments, and I hope to see you next time. Bye.